Yay. All right, so first lesson in trigonometry. We're going to start off with section 5.1 in the textbook, and it is called angles. And so we are just going to be taking a look at angles today. And yes, we are going to get started with a little bit of the unit circle for folks who know what I'm talking about. But we're going to go even more basic than that before we begin. Okay, so we're going to talk about drawing angles in what we call standard position. Okay. So here's a definition that I grabbed from the textbook. It says an angle is the union of two rays with a common endpoint. The endpoint is called the vertex of the angle, and the two rays are the sides of the angle. And so based on that, I'm wondering if we can think about how we could draw an angle from that definition, okay? So we have the union of two rays. And so if you think back to geometry, you know that you have like, if you have something like this, that is 100% not a ray, right? But we call this a line. And if we wanted a ray, what do we change about this diagram?
Is it a ray, right?
Yeah, well, how do we change it to make a ray?
Then one side would be like a point, and then it's like a arrow.
Yeah. We basically just like cut off half of it, and then we have like a dot, and then the lines on the other side of that, okay? So this is a ray. And when we say that an angle is the union of two rays, that means we're going to take the two rays and we're going to put them together, but specifically they have a common endpoint, which means that if I have one ray here and I want another ray, they should share that same endpoint, okay? And so this point right here is called the vertex of the angle. And we've heard that word before in Math 116 when we talked about the vertex of a parabola, or the vertices of an ellipse, or the vertices of a hyperbola. Okay, so that word's not necessarily new for us, but in this context, we're looking at the vertex of the angle to sort of be the pointy part of the angle. And then the two rays are the sides of the angle, okay? So we could have this one, maybe we could consider this an acute angle, all right? How would I change this to draw an obtuse angle?
Greater than 90 degrees.
So if I had one ray like this, and then I had another ray like this one we could say would be obtuse. Okay, so we have an acute angle, we have an obtuse angle, and then thinking about maybe the most important type of angle that we're going to take a look at for this class is the right angle. So we have one ray going in one direction, and we have another ray that is, that does not look perpendicular. One ray that meets the other one at a right angle, okay? And so this one is one. We're going to focus on quite a bit in this class, the idea of right angles and all the special features that come with the right angle, okay? So that's what we have for an angle. Now, as far as what we mean by in standard position, let's take a look at the graph below to help us figure that out, okay? So if I want to draw an angle in standard position, I'm going to need the initial side to be on the positive x-axis, okay? So the initial side is along the positive x-axis, right? And whatever we want to, however big we want this angle to be. So it could be an acute angle, it could be an obtuse angle, but whatever we choose it to be, let's say we had an obtuse one, maybe like this. Okay. Then this side is called the terminal side. And the terminal side is the end of the angle. Okay, so that's really where we stop. The pink side is where we start, the purple side is where we stop. And then the angle is we go from the initial side to the terminal side. Okay. Now, if I go in that direction from the initial to the terminal in the counterclockwise direction, this would be a positive angle. Okay. On the flip side, if I said, hey, let's go in the other direction. Let's start at the pink line, but let's go in the clockwise direction, like this way, okay? Then the measure of that angle would actually be negative because I'm going in the opposite direction. So our positive angles are going counterclockwise and our negative angles go clockwise. Now, most of the time we deal with positive angles, but every once in a while we throw a negative one in there, counterclockwise. And so it's important to know like what that negative sign means. It just means you're counting in the other direction, okay? So positive angles counterclockwise and negative angles are clockwise. All right. Let's talk about some special angles, okay? So earlier we said that we're going to be studying a lot about right angles. And if we think about a right angle, we know that that's 90 degrees. And in sort of the grid system that we've grown up with, that is one of the special angles that we have on our XY plane. And so if we start at the same place with an initial angle, and let's say that my first terminal side is here. So I go from the pink ray to the purple ray. How big is that angle?
Big as in the degree?
Yeah.
Yeah. Yeah, 90.
Yeah, exactly. It's a 90-degree angle. So we know that like if we started counting that we would call this 0 degrees. We would call this top one 90 degrees, okay? What if we kept going until we got to here? So
180?
Yeah, it would be 180. Exactly, 180. All right. And what if we kept going and then we stopped at the negative y-axis?
360? Oh no, that's 270. No, because 360 is all the way around.
Yeah, 270 degrees. And then when we get back here again, you're right, that's 360, okay? So 0, 90, 180, 270, 360, those are some special angles, and they're special because they fall right on the XY grid. And so we call them quadrantal angles, okay? We call them quadrantal angles. And all that means is those are the special angles that fall right on the quadrant dividers or on the axis, okay? Now, just to practice this negative angle business, what if I was counting the other way and I started here at 0 degrees? What's another name I could give 270 degrees? Yes, this could also be negative 90 degrees. So if I said, hey, I would like you to go 270 degrees, and someone else said, but I would like you to go negative 90, you would actually end up at the same place. Okay. What's another name for 180 degrees? Negative 180. Good. What's another name for 90 degrees? You got it, negative 270. And another name for 0 would be negative 360. Okay? So this is sort of, if you're like, how could you have more than one name for the same angle, like more than one measure for the same angle, then looking up modular arithmetic at some point might actually be pretty fun for you. Okay, so modular arithmetic is actually all about the study of how sometimes you could get the same number, the same equation could give you multiple answers depending on it. Yes, exactly. Okay. So far we've got a little bit of terminology. We have our initial side, our terminal side. We know that we count counterclockwise for the positive angles, but we could go the other way and count in the clockwise direction to get negative angles. And then these special ones, these quadrantal angles, we really want to know those numbers fairly well because they come up so often, okay? And so here's what we are going to do. We are going to take a look, momentarily be overwhelmed that by the end of this week, we're going to know not just what all the numbers are for this special circle, friend, but that we're going to know where all these different numbers come from, okay? Now, we're going to start simple. We're going to start with the little ovally boxes inside of here, okay? So, for example, this little ovally thing right here, okay? Inside all the little ovals, that's where we're going to put the angle measure in degrees. So if I wanted to start here, this blue circle, I would say that this is 0 degrees. Yeah. Now, based off of what we had said earlier with the quadrantal angles, I think you would all agree that this one up here is 90 degrees. And this one to the left is 180. This one down here is 270. Yeah? Are there any questions about where these 4 numbers came from? Okay. So now let's say that I'm looking at just from 0 to 90 degrees. And I happen to notice that this line right here, or that angle, is exactly halfway between 0 and 90, okay? What does that make the measure of that middle line? Yeah, it makes it 45, right? Okay. Well, let's use that idea of cutting the quadrants in half to get some of the other angle measures in here. So what about this angle, the one that is halfway between 90 and 180? How big is that angle? Yeah, 135. Okay. How about halfway between 180 and 270? $215. All right. What about halfway between 270 and 360? I don't think it's 315. Well, we're going from 270. Let's see how much are we adding every single time. So from 0 to 45, I add 45. 45 to 90, I add 45. And I keep adding 45 let's see, 270 plus 45. Is that 315? Ah, okay. So this idea that we are adding 15 or 45 degrees every single time, that's the pattern we want to make sure we see here, okay? So you were right. This 315 is correct. And what we did to get there is we just added 45 degrees every single time. Okay? All right, let's explore some of those other ones that are kind of left over now, okay? So if I start from 0 and I want to go to 90 degrees, what happens if I cut that into 3 angles that are all equal? How big is each one of those angles? Yeah, each one is 30, right? And the way that we got that is just because we're taking 90 degrees and we're cutting it into 3 pieces. So 30 degrees, 60 degrees. Okay, so 0, 30, 60. How big is this next angle going to be? 120, good, because we're adding 30 again. Okay, so 120 plus another 30 should give me 150. Okay, and so that gets me all the way to halfway around my unit circle. Okay, so how much do I add to 180 to get to this next blue line? Yeah, I'm going to add 30, so I end up with 210. Okay. I add another 30, that's going to give me 240. I add another 30, I get 270. Now you're good. I add another 30, I get 300. I add another 30, I get 330. I add another 30, I get back to 0.
Wait, would it be 245?
Where?
215 and 30?
Oh, did we make a mistake there?
I think it should be 245.
245 would make it bigger than the 240 though.
I think the 215 is supposed to be 225 degrees.
225, good catch, good catch. All right, so 225. Okay. So yeah, it can be easy to make mistakes as we're sort of adding around, but I think the bigger thing I want us to focus here on is that there are patterns. And if you can add 30 to every number and you can add 45 to a number, you know the angles inside of a unit circle. Okay. Oh, hey, you're doing some fancy arithmetic series and sequences business there. Okay. All right. So, any questions about the angle measures in degrees for the circle that we have here? Are there any questions about how we got any of the numbers in there? Okay. So let's take a look at something called a radian. Okay. So the question I have here for you is, yes, what is a radian? Okay, but maybe before we address that, I think you guys should be able to draw on the screen. Let's make sure that's true. But I'm wondering if you can draw me a picture. It could be, I don't know, maybe over here. Of what does 1 degree in standard position look like? Yeah. So if you guys can have access to the screen, let me know. Oh, okay, we got at least one person who has access. Draw an angle that is in standard position. Okay, so think about what we said earlier about what makes it in standard position. And I want that angle to be 1 degree big. Well, what do we think, folks? It looks so small. Is 1 degree that small? Maybe smaller, okay. How come something like this, how come that's not 1 degree? Okay, so we need 360 of these small measures, whatever we want to call them. We call them degrees, but we need 360 of them to make a circle. So if I did something like this, that would be, I could not fit 360 of those in a circle, okay? It could depend on how zoomed in you are. That is 100% correct. How do I save the annotations? Anybody know?
The annotations are pretty much on the Zoom call, so I guess the only way you can quote unquote save it is like either take a screenshot of the video or just draw it onto your actual notes.
Got it. Okay. All right. Well.
There's a save button, but I think it just took a screenshot.
Okay. All right. So if we're thinking about a degree in standard position, you would want the initial side to be in the positive x-axis. And then that terminal side is going to be like super close to it because we need 360 to fit in 1 rotation around the circle, okay? And so when we're looking at 1 degree, that's what we mean. And when we go back up to the circle over here, yeah, maybe we need to, this is sad. Okay. Maybe when we're looking at our unit circle again, let's take a look at what this means is that from here at 0 all the way to here at 90, it's not just 90 degrees because 90 is a right angle, but 90 of those tiny little slices that Yithan drew fit between 0 and 90. And if I wanted to know how many fit between 0 and 30 degrees, there would be 30 tiny, tiny little slices that fit between 0 and 30 degrees, okay? So that's when we think about a degree in standard position, we're really thinking, okay, they're very, very small pieces. So how does that fit in to this new word called a radian, okay? So a radian sounds kind of like the word radius, okay? And the radius in a circle is actually from the center to the halfway, the center, which is the halfway, all the way to one of the edges. And so from my center all the way to the edge, that's what we call a radius, okay? Now, if I take the radius and I cut an angle in the circle, so that these two, I think we would agree, are both radii. They're both, each of them are a radius, and so they have the same measure. So what if I told you that this radius was 3? How long would this side here be? It would be 3. Good. Okay. Well, let's say we took the length of that radius and we wrapped it right on the edge of the circle. Okay? So if you imagine, now I'm hungry, if you imagine a slice of pizza and you get a slice where the two sides of like the pizza that meet to make the vertex of your pizza slice are exactly the same length as the crust. So if the two side lengths are 3, then the crust side is also 3. Okay? If you get a special slice of pizza like that, the measure of that vertex, or the pointy part of the pizza, is 1 radian large. Okay? So is a radian bigger or smaller than a degree? Yeah, a radian, like I would rather get a slice of pizza that's 1 radian big than 1 degree big, because the 1 degree one is like really, really tiny. Whereas the 1 radian size slice is probably like a pretty good size slice of pizza. Okay? So one thing that we maybe want to write down here is that a radian is bigger than a degree. Okay? A radian is bigger than a degree. But they still measure the same things. We're still measuring how big an angle is. Okay? So if we wanted to say, go back to our degrees for a moment, we know that 360 degrees fit inside of 1 circle. Okay. How many radians fit in 1 circle? 6, okay. So I don't know how good these drawings are going to be, but if I kind of cut another slice, right? And then this would be like another radian. And then I cut another slice. And this was another radian. And then another one. And then another one. And if I did it very precisely, okay, if we sat down and drew these very, very precisely, and we measured out that the crust would equal the radius, and then we cut the pizza so that it looked like that, we would actually end up with 6 slices and a little left over. So it's actually a little bit more than 6 slices. Okay, it's a little bit more than 6 slices. There's actually a pizza place in Oakland, like in the Bay Area, that I like to go to when I visit my friends. And what I like about this place is they give you bonus slices. So when you order a pizza, yeah, I know, right? It would be so cool because you can take the pizza and go sit by the lake right by the pizza place. I think it's called Mendy. Yeah. Yeah. They have one right by Lake Merritt, and then they have one in downtown San Francisco. But Arizmendi has, they're a co-op, which is cool, which means their employees actually like own the place that they work at. But they give you, yes, they give you bonus slices. So one time I ordered a pizza and I like brought the box to Lake Merritt and I opened it up and there were like 5 extra pieces on top. I was like, this is amazing. But what I kind of think about, because I'm a math teacher and kind of a nerd, is that it's almost like they cut it into radians and then they had just like a little bit left over, okay? But we know as mathematicians that we like to be very accurate about what a little leftover actually means. And as it turns out, there are exactly 2 pi radians in one circle, okay? There are not just like 6 and a little bit radians, but there's actually exactly 2 pi radians in one circle. And if you type 2 pi into your calculator, you're gonna get about 6.28 blah, 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 okay? So it's 6 and like almost a quarter of a piece of a bonus slice, okay? So 2 pi radians in one circle. A radian is bigger than a degree. And there are 360 degrees in a circle. That's what we're used to thinking about. Now we want to think about it in terms of radians as well. We're measuring it with a different type of unit, okay? That's all a radian is. It's a different way to measure an angle, all right? Any questions? All right. Arizmendi Cafe also has like really good pastries too. If you go for breakfast, they have good pastries and coffee. Yeah, so a degree is, I would almost go the other way. A degree is like an inch and a radian is like a foot because the radian is bigger. Okay, Christina, so if you want to switch that, so you remember like the radian is bigger than the degree and a foot is bigger than inches. Okay. Yeah, exactly. Okay, so what time are we at? We're at 11 o'clock. Let's do a little bit more before we take a break, okay? So it's important to know how to go back and forth between degrees and radians, okay? And so let's talk about what we know. We know that when we count around the unit circle, that we start here at 0 degrees, and we know that the top is 90, but maybe more importantly, when we get halfway around the unit circle, we're at 180 degrees, right? And we talked about how one of these slices would be like super, super small, okay? And that would be like 1. That's my attempt at 1 degree. I think Ethan's was much better than mine, okay? But that's sort of what we're imagining, that when we go all the way around the unit circle, there are 360 of these little guys. I know, Richard. I actually, I get to cheat a lot because, you know, the tablet situation. Okay, so what's new? Well, what we have here that is a little different is we're going to start in the same place. Whoa. At 0 radians, okay? Now we don't usually, with degrees, we put the little degree symbol. With the radians, we either write rad or we don't write anything at all. And most of the time, we're not gonna write anything at all. We're just gonna give it a number, okay? But let's go back to the definition we saw earlier, that there were 2 pi radians in one circle. So what that means is that if I go all the way around this unit circle and I get back to 0, I'm at 2 pi radians. Okay, so 2 pi is kind of like 360. Well, how big is the angle in radians if I go halfway around my unit circle? We know it's 180 degrees. How many radians is it? Yeah, exactly, Isis. It's not 2 pi, but it's half of that, 1 pi, okay? So that's really where we sort of have come up with a formula for how we convert between radians and degrees, okay? And so here's what I mean by that. We know that, well, let's do this. We know that 360 degrees is equal to 2 pi radians, okay? And there's nothing wrong with using that relationship, okay? But sometimes math is easier when you work with smaller numbers, okay? Which is why in some textbooks or some videos, you'll see people say this, not 360 equals 2 pi radians, but 180 degrees equals 1 pi radian, okay? And if we break that down even further, for those of you who maybe are really curious, like, okay, so how many degrees is in 1 radian, if you want to sort of visualize it? 1 radian is about 57.3 degrees. So it's like almost 60 degrees, but not quite, okay? Now, I would say of these three, the most important one that kind of helps us figure out all the different angle measures would probably be the middle one right here, okay? This pi equals 180. And so what we do when we try and convert between radians and degrees is we actually just set up a ratio, okay? So what we're going to do is we're going to have a ratio of the degrees is going to equal the ratio of the radian. So if I know there's 180 degrees in 1/2 of a circle, I know there's also pi radians in that half of a circle. So like 180 is the same as pi. Now in the numerators, this is where you're going to be able to use this for like every kind of angle conversion. Above the 180, we're going to put the angle in degrees, okay? So whatever the angle in degrees is. And then above the pi, we're going to put the angle in radian, okay? And so this formula right here will help you go between radians and degrees with not too much difficulty, okay? And so let's just kind of practice with a couple examples, and then I will set you guys off for a break, okay? So everybody got this formula copied down? Hey, okay, so we're gonna use this formula and we're gonna take a look at a couple questions. All right, so we're gonna look at these 3 questions right here and then we'll take a break. So for each of these questions, I want us to be able to draw a picture. So I want us to know how big that angle is or what it looks like and how to draw them. I want to know the angle measure in degrees, but I also want to know the angle measure in radians, okay? And so let's go ahead and start off with this very first question. So the first line is that you're given pi over 9 as the angle measure in radians. So we might even say that this is my theta radian, okay? Theta, by the way, is what we tend to use when we call an angle, all right? So I think I skipped this part, but it's basically like an O with a line through it, okay? And we read this as theta. And it's mostly used to describe an angle. So usually when you see theta, they mean an angle, okay? So if I'm given the angle measure in radians and I want to find the angle measure in degrees, then what we could do is set up our ratio. So I know I always put 180 on the bottom, and I always put pi on the bottom of the other side, okay? Now, where do I put the pi over 9? Do I put that over the pi or over the 180? Okay, you say over the 180. Why do you say over the 180? Maybe I wasn't very clear about my question. Let's scroll up for a second. Okay, so if we have an angle in radians, then we put it over the pi, okay? And if we have an angle in degrees, we're going to put that over the 180. So the pi over 180. Yes, it will. The pi's will reduce eventually. Yeah. Okay. Thank you for clarifying. All right. So it's going to be pi over 9 all over pi equals my theta in degrees over 180. Okay. So it's almost like terms on both sides. We've got our degrees on one side and we've got our radians on the other side, okay? Now, the tricky thing is, and this is why I wanted to start with this question, is like, how in the world do we reduce this right-hand side, okay? Yeah, I think it's hard, especially if you write your zeros like this, which is another Greek letter also. I would recommend if you write zeros like this that you would stop doing that soon if you plan to go super far in math. But everybody finds it their own way to write things. So. Okay, so let's simplify this right-hand side here. What we could do is we could take the idea of dividing a fraction and knowing that's the same thing as multiplying by the reciprocal. Meaning I have pi over 9 times, if I'm dividing by pi, it's the same as multiplying by what? I'm dividing by pi though. So I need to multiply by not pi over 1 over pi. It's the reciprocal of that bottom. Yeah, okay. And then if we wanted to combine these two fractions, what would that simplify to? Yeah, 1/9. I think a lot of us can see that this pi and that pi are going to reduce, and that will get 1 over 9. And so really we have theta over 180 equals 1 over 9. Okay? And now we can multiply both sides by 180, get rid of that, and then we'll get 180 over 9, or that's going to give us 20 degrees. Okay? So pi over 9 is the same as 20 degrees. So I might not know what pi over 9 looks like, but I bet we can all approximate a drawing of 20 degrees, right? The only catch is we got to make sure it's in standard form. So we're going to draw ourselves an axis. And another axis. And then we're going to have our initial side. And we're going to have our terminal side, and we're going to have that. And we know that this is 20 degrees or pi over 9 radian. Okay. Questions on that first one? Okay. I think this is the hardest out of all three examples, okay? All right, let's take a look at the second one. We have 160 degrees in standard form. We can actually go ahead and fill out my angle measure in degrees, right? The diagram tells me it's 160 degrees, that's pretty straightforward. But the work now for us is to convert 160 degrees into radian, all right? So we know that we can set up the ratio, all right? What are we going to put on the degree side of the ratio? We're going to have 160, and more specifically, 160 over 180. Good. And then on the other side, we'll have our theta radians over pi. Right? So that 180 and that pi are our constant denominators when we're converting back and forth. All right, let's take a look at this fraction right here, and let's reduce it. When we reduce 160 and 180, what do we get? 8/9, okay. So I kind of like to take it step by step. I could reduce this to 16 over 18. Yeah, and then I notice they both are divisible by 2, and then I'll get to thea's 8/9. So I get 8 over 9 equals theta radian over pi. Okay. And then what's my last step to get the theta radians by itself? Multiply by pi. Good. So theta equals 8 pi over 9. I tend to put my pi in the numerator. You can also write it like 8/9 and put the pi next to it. That's sort of a personal choice. I think it depends on like textbooks and whatever professor you have, but these two are fairly interchangeable. Again, I tend to do the first one, but you're welcome to do the second one as well, okay? So I think it's a little easier to go from degrees to radians just because you don't have like the fraction inside of another fraction, okay? But we've got one last question here, which is negative 315 degrees. And so let's kind of start with a diagram and see what that gives us. So if I have my initial side here, which way should I count the angles? Should I go clockwise or counterclockwise? Clockwise, good, yeah. So that means that I'm gonna count in this direction, and I gotta go 315 degrees in that direction, and that should land me right about here, okay? So if I want to label this as negative 315, what I should do is start from the initial, go all the way to the terminal, and then label that as negative 315, okay? What's another name for negative 315 degrees? Like what's another angle measure I could call it in degrees? Yeah, 315 is negative 315. It's the same as 45 degrees, okay? So I'll write that here, same as 45 degrees. All right, Now that's going to be important as we start to work through the questions, is being flexible about what name we call an angle. Most of the time we're going to give it a positive name, but once in a while we're going to give it a negative name. Okay? All right, let's set up this ratio. I've got negative 315 over 180 equals my theta radians over. Okay. So some of us, again, might be really good at the mental math here, but just to kind of talk through some steps in terms of reducing, I think like a good number to divide everything by might be 5. So if I divide 315 by 5, I'll get 63. If I divide 180 by 5, I'll get 36. But I think I can reduce that more. What number goes into 63 and 36? I think 9 does, yeah? 9 goes into 63. How many times does 9 go into 63? Yeah, 7, okay. So 7 over 4, and that's pi over theta over pi, and let's not forget that negative sign, right? Negative 63, so it's a negative 7 pi, or 7 over 4. And so when we get our final answer, we could write it as negative 7 pi over 4, or negative 7 over 4 pi. Okay. All right. Any questions on going back and forth between the diagrams, the angle measures in degrees, and the angle measures in radians? So I think this is a good time to take a break. So it is 11:19. Let's be back here at 11:30. Okay, let's meet back here at 11:30. So I'm going to stop sharing my screen. Yes, we're looking for lamps. We're looking for lamps. I love that. Okay. So I know that it's kind of hard to see the bigger picture sometimes, especially with things that you have not seen before. It seems like a lot of you have seen this idea of angles and converting between radians and degrees. But as you can kind of tell, like, it's not necessarily a hard process, but it can get kind of cumbersome, especially if we're thinking we want to go back to our unit circle that we filled in earlier. We did all the degrees, but now we want to do all the radian measures. And so we could sit and convert how many? 1, 2, 3, 4, 5, like 20 different angles. We could convert those and do that same process that we did in example 1 for every single one of these angles, right? So the radian just means the angle, like how big is the angle at the pointy part of the pizza. So we're not talking about area, it's just another way of measuring how big an angle is. Okay. So when we were kind of thinking here, right, when we were talking about 1 radian, the radian part is like this angle. Right, it's not a degree. I think Christina said it really well earlier. She said like a degree is kind of like an inch. Like you could measure how long something is in inches, or you could measure how long it is in feet. So radians is kind of like measuring something in feet, whereas degrees might be like measuring something in inches. Okay. Cool. All right. So since I think that we don't want to sit and do every single one of these and figure out like how big it is in radians, what we're going to do instead is talk a little bit about a potential shortcut for converting angles. Okay, and so this kind of goes into what folks were saying earlier, that like sometimes a lot of the numbers start to look the same. Okay, but before we get there, I actually want to fill in, let's see, how can I do this? I actually want to fill in some of the, oh no, that's not good. Oh wait. We're going to fill in some of the radian measures. Whoops. Okay, that we already know so far. Okay, so we know at 0 degrees, this is also 0 radians, right? And how many radians is it when we get to 180 degrees? So let's kind of go back up for a moment to our unit conversion, right? We said when we looked at these pictures, yeah, that 0 degrees is like 0 radians, but 180 degrees is like pi radians, or 3.14 radians. Okay. And so let's go back down and let's start to fill in some of those. And let's actually stick to the same color we used before. So we've got 0 radians, we've got pi radians. Okay. Any guesses as to how many radians is the same as 90 degrees? Okay. How did we get that? Why is it a half a pi? You're all right. Yeah, half of 180 is 90, and half of pi is pi over 2. Good. Okay. What about this angle right here? The one that's halfway between 0 and pi over 2. How many pi's is that? Yeah, we could say this is a quarter of a pi. Okay. So let's just kind of stop here for a moment. We could fill this in thinking about it like fraction, okay, or parts of a whole. And I know a lot of times when we talk about fractions, people kind of start to get like nervous, get a little sweaty, like, you know, it makes people like a little anxious when we talk about fractions. But let's do a little throwback to like elementary school math, okay? So I think we've all seen questions like this. You have a candy bar and you want to split it equally between 4 friends, right? If you give away one part of that candy bar, what fraction of your candy bar did you give away? 1 out of 4, right? The 1 comes from the shaded part, and there's 4, like 1, 2, 3, 4 pieces, right? So it's 1 out of 4 pieces. Now, what if you had a candy bar and you cut it into 4 pieces because you thought all 4 of your friends wanted, or all 3 of your friends wanted a piece, but then 2 of your friends were like, I don't really want any, I'm all set. So then you take the candy bar and you're like, I'm gonna just split this with my 1 friend. So you get 2 pieces and they get 2 pieces. So as an unreduced fraction, what fraction of your candy bar did you give away? Yeah, 2/4, right? 2/4. And I think we're at a place where we're like, 2/4 is definitely the same as 1/2. So we usually write 1/2, right? Okay, what if we had, I don't know why that candy bar got bigger. We have one candy bar and now we have more friends. In fact, there are 6 of us all together. I mean, if you put it in the microwave, technically it gets back together, I think. So let's say that we got 6 people who are all sharing this candy bar, and one person takes 1 piece. What fraction of the candy bar did that person take? Yeah, 1 out of 6 slices, right? Yeah, basically. You're like, what's another name for this? Okay, what if you decide, oh, I'm gonna cut it into 6 pieces, but then there's only 3 of you. And so each person gets how much of the candy bar? Yeah, they get 1/3, but what was that before you reduced it? 2/6, yeah, 2 pieces out of the 6 pieces that you cut, okay? And then let's say you bring the candy bar and only one other person shows up, so you split it this way. I think we would agree that unreduced, you gave away 3/6 of your candy bar. But if we reduced it, we would have given away half of our candy bar, right? So a few ideas here, that when we are dividing things into pieces, we need to look at how many we have out of the total, right? So in the first picture, we gave away 1 out of 4. The second picture, we gave out of 2 out of 4. The third picture, we gave 1 out of 6. The fourth picture, we gave away 2 out of 6. And the last picture, we gave away 3 out of 6. Now, some of them we could reduce, so we reduce them, right? Nobody says 2/6, everybody says 1/3. Or nobody says 2/4, everybody says 1/2. And nobody says 3/6, they say 1/2, okay? The last picture that I want to draw you is just to kind of drive home this idea of what we mean when we're talking about fractions, okay? So let's say that I have, I'm sharing my candy bar with 3 other people. So there's 4 of us. So I'm like, okay, everybody gets a piece. But I cut it like this. And then I claim that I gave away 1/4 of my candy bar. Valid or not? Okay. Why do we say that last picture does not represent 1/4? Because isn't it like the first picture? Like I cut it into 4 pieces and then I shaded one of them. So that's 1/4. Ah, okay. Because this is not divided up equally. So that's one thing we want to be really careful of. This is not true because the pieces are not equal. Okay, so this is the last one is not true because I randomly cut it, like Sia says, I randomly cut it. The pieces are not equal. So I can't say that's 1/4 of my candy bar. Okay, in order for us to do fractions, like we're thinking about dividing things into the same size piece. Okay, so when I say 1 out of 4, all 4 pieces better be the same. If I say 1 out of 3, all 3 pieces better be the same. If I say 2 out of 4, all 4 pieces need to be the same, okay? So that is really, like when we talk about fractions, that's really the gist of what we mean. We got a part, we have a whole, and we're cutting it up into equal pieces. And then however many slices we take or how many pieces we take, that gives us the top number. And then the bottom number is just how many there were to begin with, okay? And then the last note is if we can reduce, we should reduce. But if we can't reduce, then we leave it that way. All right, so we're gonna do the same kind of question, but with a half a circle. No. Okay. Richard, you should see my diagrams in a live class. They are so not good, okay? Do not be fooled by the diagrams I'm able to create here. Okay, so let's call this 0 and let's call this pi. And I'd like us to divide this into 4 equal slices, okay? And so I could do it in a number of ways, but maybe the easiest way is to cut it in half. And then to cut each half, this is really bad, in half again, right? If I wanted 4 equal pieces of a half a circle, I could divide them this way. And this is kind of how we see like a traditional pizza pie gets cut into like 8 slices, right? So we get 4 from 1/2. So if I know from 0 to pi is the whole thing, then you guys were right that this top one is half a pi, okay? But maybe before we get to that half a pi, this one is 1 pi over 4, because it's 1 out of 4 slices. This one, how could I call that one if it was unreduced? 2 pi over 4, right? How could I call the third one? 3 pi over 4. Good. Okay. How could I call pi if it wasn't reduced? Yes, I love it. 4 pi over 4. Okay. So I know some of you are like, why is she not reducing these? These are so much easier to write them as pi over 2 or pi. But the point I want you to see here is that there's a pattern. Because if I now include the bottom half of my ugly circle and I divide the bottom half into 4 slices, okay, what does that make this angle? Yeah, 5 pi over 4, because I just kept adding. Okay, if this is 5 pi over 4, this bottom one would be 6 pi over 4. This last one would be 7 pi over 4. And the last one would be 8 pi over 4. Okay, so when we're looking at angles in our unit circle, we can think about it just like our candy bar example. We can cut the half of the circle into as many slices as we want, and then we literally count around. And after we've counted, then we can reduce. We can say, hey, I know this is really pi over 2. I know this one is really pi. What's another name for 6 pi over 4? Yeah, 3 pi over 2. And what's another name for 8 pi over 4? 2 pi. Good. And so when we're coming up with these angles on our unit circle, they really go back to the idea of a fraction. If we want to cut these into equal size slices, like 4 on the top and 4 on the bottom, then we count by pi over 4. And if we can reduce, we reduce. And if we can't reduce, we leave. So let's go ahead and fill these angles in on our unit circle. Okay. So we had said, whoops, I was in the wrong place. We had said the one that's halfway is 1 pi over 4. Okay. 1 pi over 4. This one was our 2 pi over 4. 3 pi over 4. The pi is secretly a 4 pi over 4. 5 pi over 4. We said this was 3 pi over 2 because it got reduced. And then our last one, this one was 7 pi over 4. Okay. So what we did here, like where these green numbers come from, is not different than when we're thinking about the candy bar example. The only difference is we're looking at slices of the half circle. Okay, slices of the half circle. All right, let's go back to that half circle example. Okay, let's go back to that half circle example. And this is what I'm going to have you pop out into some breakout rooms and do a conversation about, okay? So what I want you guys to talk about in your breakout rooms is if we take a half a circle, that's so bad. Okay, that's better. If we take a half a circle and we were to cut it into 6 slices, so not 4, but 6, it might look something like this. That would be 2 slices. And then I've got 3 in one half and 3 in the other half. Okay? I know this is 0. What would I call this side in its unreduced form? Six pi over 6. Okay? Because I've now cut it into 6 slices and I got all 6 of them. 6 pi out of 6. So what I'd like you to do in your breakout rooms is to figure out the angles that all go in between. Okay. Do the top half of your unit circle. Make sure everyone in your group feels comfortable with that, where it came from. Then do the bottom half of your circle and fill in all the other green angles on the inside of the unit circle. Do not worry about the outside of the circle. I want us to focus on the inside of the circle. Okay? Are those directions clear? You're going to figure out those other angles, all right? Now, I know you can just Google a unit circle. You might already have one up on your screen or from your binder from high school. But what I want us to do is go through this exercise of like visualizing what we're actually doing, okay? All right, so we wait for everyone to come back to the room. All right. So hopefully you had a little bit of time to kind of think about it visually. But I think one of the things that's very confusing for students is like, how come some of the fractions have to be over 4? Some of them are over 6, or some of them are over 3, and some of them are over 2. And I think what it boils down to is that you have different slices that you could take of the top half of the unit circle. So if you cut the top half into 2 slices, that's where your pi over 2 comes from. If you cut the top half into 3 slices, then you get the pi over 3s. You cut it into 4 slices, you get pi over 4. You cut it over 6, you cut it into 6 slices, you get the pi over 6. But it's not consistent because some of them reduce and some of them don't, okay? Some of them reduce and some of them don't. And so that's why some of them are over 3, when you counted, it could have been over 6, okay? So some of you might have thought, oh, pi over 3 was really where 2 pi over 6 came from, and that's true, okay? Another name for pi over 3 is 2 pi over 6. But we tend to keep things in its most reduced form, which is where we get the pi over 3 from, okay? So if you've learned the unit circle before, I hope this gave you sort of a new view on where these things come from. If you've never learned the unit circle before, I think this was definitely a lot in terms of like thinking about it in terms of fractions. But hopefully it'll give you a little bit of an understanding as to where all the different numbers come from. Okay, at the end of the day, it's important that we know how to use this tool, but I think it's useful to think about where it came from as well. All right. Are there any questions before we move on to the next part? Oh. Okay. All right, so let's move along. All right, so one thing that was kind of hinted at the beginning of the class was this idea that, yeah, we have a circle and we can kind of go around the circle as many times as we want. But a lot of them boil down to the same angle. Like we said, negative 315 was the same as 45 degrees, okay? A lot of our angles had more than one name. And so that's where this idea of coterminal and reference angles come from, okay? So coterminal angles are two angles in standard position that have the same terminal side, okay? So for example, if I started here, so standard position means they start the same place. And let's say they both end here, okay? But in one version, maybe we just counted this way. That would be like a positive angle, right? But another way we could name this angle is we could go in the negative direction, okay? So we've got sort of the positive and the negative. Those are always two names that you can give for the same angle, okay? And another way we could think about it, and this is where the diagrams kind of look a little funky, is that maybe we actually have the same starting and ending side. So initial and terminal, but let's say we want to go more than one time around the unit circle. And so if we go in our counterclockwise position, it might look like this. We might go like, we go one time, it kind of looks like a snail, okay? Or like a spiral, but that's one time around the unit circle. And then I decide to stop at the terminal side, okay? So, oh, hi. Which angle is bigger? This blue one or this blue one? So the blue one with 1 star or the blue one with 2 stars? Which one is a bigger angle numerically? Yeah, the one with the 2 stars, right? Because I went around the circle another time. Now, I could even go around the circle like 3 times. That would be okay. Gosh, my diagrams are getting terrible. Okay, so here's my initial side. Here's my terminal side. I could go around the circle, let's see, 1 time. Well, 1 time. Another time. Another time. And then I decide to stop. Blue angle with 1 star, blue angle with 2 stars, blue angle with 3 stars. I think we would agree that the blue angle with 3 stars is even bigger than the other one because I added 360 degrees every time I went around the circle, okay? But I think we might also agree that the purple line and the pink line all kind of have the same angle in between in all of the 3 pictures, okay? And so that's where this idea of the reference angle comes in. So the reference angle is a fancy way of saying the smallest acute angle formed by the terminal side and the initial side. So this one right here is our reference angle. Okay? And all 3, the light blue one, the blue one with 2 stars, the blue one with 3 stars, those are all coterminal to this reference angle. Okay? And so that's what we mean when we say coterminal and reference. Okay, so reference is the smallest one. It's usually the handiest one to work with. And the coterminals are just like these other names that we could give the angle if we wanted. Okay? So I pulled this from your textbook as well. All right, so we've got how to. So one of the things in your textbook, if you haven't started reading it, is they do give you steps on how to solve specific problems, okay? And a lot of times I pull from these methods to go over in class, but if you like them to be written out in a very straightforward way, it might not be a bad idea to take a look at these parts of your textbook. And so in this case, the how-to says, given an angle greater than 360, how do we find the angle that is coterminal, which means it has to be between 0 and 360, okay? So here are the steps they give us. They say, subtract 360 from the given angle. If the result is still greater than 360, you subtract 360 again. You basically keep subtracting until you get a number between 0 and 360. Once you're between 0 and 360, that is your coterminal angle, okay? So let's give this a try with example number 2 here. We've got 900 degrees. Now 900 is definitely more than 360, okay? So the question is, how many times did I go around the circle extra? So 900, let's see, they tell me to subtract 360. Okay, 900 minus 360 is what? 540 degrees? Okay. Do I need to subtract 360 again? Or am I done? Yeah, I need to keep going because the directions say if the result is greater than 360, subtract it again. So now I'm going to do 540 minus 360. And what does that give us? 40, 180 degrees, is that right? Did I do that right? Yeah. Yeah, it's 180, okay? Am I done? Yeah, because my answer is between 0 and 360. So that means that 180 is, nope, wrong order. 900 degrees is coterminal to 180 degrees, okay? Meaning that if I stopped at 180 or I went around the circle 2 times and then I stopped at 180, I would be at the same place, okay? So this means I went 2 extra times around the circle, okay? All right, So I want to play a little bit of a what if, because how do we apply this to example 3, right? This says that I subtract 360 from the given angle. So if I do this, negative 200 minus 360, well, I'm going to get negative 560. And then I might be like, well, that's not between 0 and 360, so let me subtract it again. Negative 920. Is this heading in a good direction for me? Am I gonna get closer to a number between 0 and 360? No, right? We can tell just by trying that this method is not working for us. So what do you think we might, okay, Brian, you try it, you let us know what you get, okay? If I keep subtracting 360, I'm gonna get a number that is continually more and more negative. All right, we'll see you in a bit. How do you think that we might shift our strategy in order to accommodate for the fact that this is a negative angle? Yeah, we add, okay? Yes, you could do that as well, for sure. So let's shift our strategy. Instead of subtracting, let's add. All right, negative 200 plus 360 is going to give me 160. Am I done? Did I end up with a number between 0 and 360? Yeah. Okay. So one of the things that I think I've noticed on a lot of the reference sheets is sometimes people write down like different cases as just totally different. And one thing I would encourage you to do is like you could take these directions and you could modify them, and you could make yourself a note that like for angles, nope, for negative angles, you add 360, right? That would be a really easy way to make an addition to your reference sheet so that you can get more than one sort of rule on the same problem, right? So you can subtract it if it's bigger than 360, but if it's a negative angle, then we want to add 360 until we get there, okay? But how would we modify this for questions like 4 and 5? I've got 11 pi over 3 and I've got negative 21 pi over 9. If I add 360 or I subtract 360, that's going to be weird looking, right? But yeah, I think that's a great idea, Theo. We could, instead of saying add or subtract 360, if it's in radians, well, let's do it in radians. If it's in radians, let's, instead of adding 360, what do we call 360 in radians? We call it 2 pi. And so maybe another note that you could write for yourself is for radians, you could add 2 pi or subtract 2 pi, right? This would be for like a positive angle. Oh no, sorry, a negative angle, or a positive angle. Okay. So this is an example of like how you can take one piece of the textbook or one part of the steps that we do in class and modify it so that it fits all of the cases that you might get asked about. Okay. So again, thinking about how do you make those decisions. All right. So let's do one of these real quick. So example number 4. If I want to get this to be its coterminal angle, 11 pi over 3, I'm going to subtract 2 pi. Okay. But what would be a better way of calling 2 pi so I could subtract it fairly easily? Yeah, let's call it 6 pi over 3, right? Let's reduce that fraction, because now they have a common denominator, and look, 11 pi over 3 minus 6 pi over 3 gives me 5 pi over 3. Is 5 pi over 3 between 0 and 2 pi over and 2 pi? Yeah, it is, right? Because 2 pi is really 6 pi over 3. So 5 pi over 3 is less than that. So we're good. Okay. Now, how would we modify this for example 5? I've got negative 21 pi over 9. Is this an okay setup? Yeah, we want to add, right? We want to be training ourselves to make that decision from the get-go. And I'm going to add, but I'm also going to change 2 pi into 18 pi over 2. Because I'm thinking, what is the unreduced form that will get to 2 pi? Yeah, I think Brian's going to sit and try this one too. Let us know how that goes. All right, so if I add these, I'm going to get negative 3 pi over 9. Is that between 0 and 2 pi? And I think we're going to say no, right? Negative 3 pi over 9 is not between 0 and 2 pi. So I have to add it one more time. Negative 3 pi over 9 plus 18 pi over 9 gives me 15 pi over 9. And now I'm good to go. Okay. Any questions about how we took the one how-to from the book and extended it to all the different cases that we have here? All right. All right, so we already talked about this, extending the how-to to fit all of the cases, but I just want to make sure that you know this could be a good strategy to apply for a reference sheet or just studying in general. Like, if I know how to do this one problem, how do I do another problem that kind of looks like it, but something got changed, okay? That's just a really helpful way of thinking about the math that we do, okay? All right. Hey, Val, are you there? Oops. I told her 12:25. Thanks, Richard. Okay, so here's what I'm gonna do. We'll hang out here until Val pops in. She should be here in about a minute. I'm gonna make a video for this last part here. I don't wanna sort of smash it in at the end, but I'll make a video and post this for this last section when talking about length of an arc and area of a sector. And that will help us finish up this first section 5.1, okay? So I'm gonna pause this right here.